This video is about the correspondence theorem for groups. Our goals for this video are to state and prove the correspondence theorem for groups, work a few examples, and provide several concept checks. We will use these notations for n is a subgroup of G, n is a normal subgroup of G. For an integer n greater than or equal to 2, Zn will stand for the additive group of integers modulo n. Dn will denote the dihedral group of order 2n, with a rotation element A and a flip element B, such that a to the n equals b squared equals e, and ba equals a to the n minus 1b. Sn will denote the symmetric group of order n factorial. We'll express elements using cycle notation. And an will denote the alternating group of even permutations of Sn. We're going to start with the following useful lemma. Let G be a group, and let n be a normal subgroup of G. Then every subgroup of G mod n is equal to H mod n for some subgroup H of G containing n. In order to prove this, let S be an arbitrary subgroup of G mod n. Consider the set H consisting of all of the elements x in G such that the left coset xn is an element of S. This turns out to be the H that we are looking for. We will show that n is a subset of H, that H is a subgroup of G, that n is a normal subgroup of H, and that S is in fact equal to H mod n. And this will complete the proof. So for the first part, we need to show that n is a subset of H. This is fairly easy. Let A be an element of n. Then the left coset, an, is equal to n, which is the identity element of G mod n, and therefore an belongs to the subgroup S. Thus, by definition of H, A belongs to H. And therefore, n is a subset of H. For the second part, we need to prove that H is a subgroup of G. This is elementary as well. We have n is an element of S, so E is an element of H. Thus, H is non-empty. Given H1 and H2 elements of H, then by definition, H1n and H2 inverse n will belong to S. But then the product of these two cosets, H1, H2 inverse n, belongs to S. And therefore, by definition, H1, H2 inverse belongs to H. And therefore, H is a subgroup of G. N inherits the normality in H by virtue of n being a normal subgroup of G. That is, if you let A be an element of n and K be an element of H, then K is an element of G. And so conjugating A by K will result in an element belonging to n. Therefore, n is a normal subgroup of H. And finally, we need to show that S is equal to H mod n, but a coset xn belongs to S if and only if x belongs to H, by definition of H, which is true if and only if xn belongs to H mod n. And therefore, we have shown that S is equal to H mod n. Here's our first example. Let G be Z12, and let n be the subgroup consisting of 0 and 6. Subgroups of Z12 mod n by the lemma are of the form H mod n, where H is a subgroup of Z12 and n is a subset of H. If we look at the lattice of subgroups of Z12 containing n, we get this picture. Now I'm actually showing you the lattice of all the subgroups of Z12 just for comparison, but the trivial subgroup and this subgroup K consisting of 0, 4, and 8 do not contain n. The subgroups that do contain n are n itself, Z12, and these subgroups H1 and H2 given here. H1, the subgroup generated by 2, and H2, the subgroup generated by 3. So, by our little lemma, the subgroups of Z12 mod n are Z12 mod n, H1 mod n, H2 mod n, and n mod n. And you can see that the lattice of subgroups of Z12 mod n is identical to the lattice of subgroups of Z12 containing n. So notice that correspondence between the subgroups of Z12 containing n and the subgroups of Z12 mod n. In fact, the indices match as well. The index of each subgroup inside the larger group matches the corresponding index of the corresponding subgroups of the quotient groups. So this is no coincidence. Here we are with our main theorem, the correspondence theorem for groups. Let G be a group, and let n be a normal subgroup of G. First, there is a one-to-one correspondence between subgroups of G containing n and subgroups of G mod n. And there's actually a second part. In the correspondence, normal subgroups correspond to normal subgroups, meaning that if a subgroup H of G containing n is normal in G, then H mod n will be normal in G mod n. So let's start the proof. By our useful lemma, every subgroup of G mod n is equal to H mod n for some subgroup H of G with n contained in H. So let A be the set of all subgroups of G containing n, and let B be the set of all subgroups of G mod n, and consider the function f from A to B, taking each H in A to H mod n in B. F is well defined and surjective by our lemma. So it remains to show that F is one-to-one. Let H and K be subgroups of G containing n, and suppose H mod n equals K mod n, we must show that H equals K. For the forward containment, let R be an element of H, then the left coset Rn belongs to H mod n, which by hypothesis is equal to K mod n. Thus Rn equals Sn for some S belonging to K. Thus, S inverse R belongs to n, but n is itself a subset of K, so therefore S inverse R is equal to T for some element T of K. Thus, R equals St, which belongs to K. Thus, H is a subset of K. The reverse containment follows exactly the same way, just reverse the names H and K. And I want to make a little remark about this argument right here. You'll see this argument quite a lot. It follows from this nice little result that says that the coset Rn belongs to K mod n if and only if R belongs to K. And you can see that I have reproved this result, or at least the forward direction of this result right here. So I'll actually use this result again later in the video, but to keep that in mind, that that is a common argument. Part 2, which says that normal subgroups correspond to normal subgroups. Let's prove that. So let H be a subgroup of G containing N. We're going to show that H is normal in G if and only if H mod N is normal in G mod N. In the forward direction, suppose H is normal in G. Let Xn be in G mod N, and let Yn be in H mod N. Then when we conjugate Xn by Yn, we get Yx Y inverse N, which belongs to H mod N because H is normal in G. In other words, we have X as an element of G and Y as an element of H. And so if we conjugate X by Y, we should wind up back in H because of the normality of H. And therefore Yx Y inverse N is an element of H mod N, which shows us that H mod N is normal in G mod N. In the reverse direction, suppose H mod N is normal in G mod N. Pick an arbitrary element X of G and Y of H. We want to conjugate X by Y and make sure that we wind up back in H. Well, so then Yn, Xn, Yn inverse is Yx Y inverse N. Now this belongs to H mod N because H mod N is normal in G mod N. So therefore, and here's this lemma that we referred to on the previous page, that Yx Y inverse N belongs to H mod N. That must mean that Yx Y inverse belongs to H. We reprove that argument here. But the upshot of it is that we have just proved that H is normal in G. Here's your first concept check. I urge you to pause the video and work out the answer for yourself before proceeding. Let G be that dihedral group of order 8, D4, and let N be the subgroup consisting of E and A squared. N is a normal subgroup of D4. You can note that N is actually the center of D4, and the center of a group is always a normal subgroup. Now consider H to be the subgroup generated by A. Again, that is E, A squared, A cubed, because A is our rotation element of order 4. Now we can note that N is a subset of H. And the questions for you are, find H mod N, what is in this group, and is H mod N normal in D4 mod N? So pause the video and come back when you have an answer. Okay, so here is our solution. Note that H is of order 4 and N is of order 2, so the index of N in H is 2. So that means H mod N has only 2 elements in it, and one of them is the identity. So we have N, which is the identity element, and then we just have to pick one other element that is not in N to make a coset with, so I chose A, to make the coset AN. And that's H mod N, N and AN. For part 2, I claimed that H mod N is normal in D4 mod N. We can see that the index of H in D4 is also 2 because D4 is of order 8 and H is of order 4. So by the index 2 theorem that says that any subgroup of index 2 is normal, H is normal in D4. Thus, by the correspondence theorem, H mod n must be normal in D4 mod n. As an additional remark, note that the index of n in D4 is 4, and thus D4 mod n is a group of order 4, and therefore must be abelian, and therefore all subgroups of D4 mod n are normal. If we compare the lattice of subgroups of D4 containing n with the lattice of subgroups of D4 mod n, again you can see that they are identical. This is confirmed by the correspondence theorem, but here it is in a specific example. You can feel free to pause the video to look at more details here. Here's our other main example for this video. Let G be S4, the symmetric group of order 4 factorial, and let n be the subgroup shown here, the identity, the permutation 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. Now S4 is quite a complicated group. Look at this beautiful subgroup lattice. So this is a complete subgroup lattice for S4, but luckily we're only going to look at a part of it because we are only interested in the subgroups of S4 that contain n. And this here is our n. So we're only going to see this part of the diagram. So here it is. First of all, let's note that n is normal in S4 by the cycle shape theorem, which says that conjugation preserves cycle shape. N consists of all of the elements of S4 that have this cycle shape, namely two cycles when expressed as a product of disjoint cycles. And so if you conjugate anything in n by anything at all in S4, you will wind up back in n. Now let's analyze the other subgroups of S4 that contain n. A4, the alternating group, is normal in S4, again by the index 2 theorem. So by the correspondence theorem, A4 mod n is normal in S4 mod n. So that leaves these other 3 subgroups here. What are they? Well, they are these groups right here. H1, I'll call H1 the subgroup generated by n and the cycle 1, 2. In other words, if you multiply everything in n by 1, 2, and by e, you will get these 8 elements here. The first 4 of which you can recognize as the elements of n, and then the other 4 are what you get when you multiply elements of n by 1, 2. Similarly, let H2 be the subgroup generated by n and 1, 3. And let H3 be the subgroup generated by n and 1, 4. And clearly, these all contain n. And they're all of order 8. You can note that each of the HIs is isomorphic to D4, since HI is non-abelian of order 8, and HI contains exactly 2 elements of order 4. And that's enough to classify it as being isomorphic to D4. Again, you're invited to pause the video to convince yourself of these details before going on. So here's our big question. Are these subgroups normal in S4? So here's, again, an opportunity to pause the video. Given G and N and H1 as above, is H1 normal in S4? Pause the video and come back when you're ready. Okay, so the answer is no. For example, if we conjugate 1, 2 by 1, 2, 3, we end up with 2, 3, which is not in H1. And you can come up with similar counterexamples to show that H2 and H3 are also not normal in S4. Thus, by the correspondence theorem, Hi mod n is not normal in S4 mod n for each I from 1 to 3. So here's what we've discovered. The lattice of subgroups of S4 containing n is identical to the lattice of subgroups of S4 mod n by the correspondence theorem. And moreover, the normal subgroups correspond to the normal subgroups. So you can see here, these are our H1, H2, and H3. They are not normal in S4. N and A4 are normal in S4. Correspondingly, over here, we have H1 mod n, H2 mod n, and H3 mod n as subgroups of S4 mod n. Those are non-normal subgroups. And we have A4 mod n and n mod n, which are normal in S4 mod n. The indices also match up. The red dashed lines represent an index 2 subgroup, and the green solid lines represent an index 3 subgroup. And it's the same in both lattices. So in summary, we've proved the correspondence theorem that says that given a group G and a normal subgroup N of G, there is a one-to-one correspondence between subgroups of G containing N and subgroups of G mod N, given by the correspondence here, H corresponding to H mod N. And in the correspondence, normal subgroups correspond to normal subgroups. I hope you found this video helpful.